Right, good morning everyone. We're having a look at solving vectors simultaneously today. So it's based on what we were doing yesterday. We saw that we can relate three-dimensional vectors to two-dimensional lines and equations, and just like you can solve lines simultaneously, we're going to be having a look at how we can solve vectors simultaneously as well. So let's have a look at this first of all. When we were creating the equations yesterday of vectors, we used t as a scalar parameter. If you've got two or more vectors, you can't use t for both of those vectors, it gets too confusing. So typically what we're going to do is have one vector that has t as the scalar parameter and the other vector to have s. Now much like when we're using normal algebra and solving normal simultaneous equations, sometimes we don't use letters, sometimes we'll use Greek symbols. So we could use, for example, that's the t and s, we could use, for example, alpha or mu or alpha and beta, we can use epsilon, we can use any of the Greek symbols as well. All right. Are you happy with this being the three-dimensional equation for a line, also a vector? Happy with those? Right, so what we're going to look at today is how we can solve them simultaneously. It's based upon what we did yesterday, we're just taking it a couple of steps further. Right, so it's important to know that in 3 dimensions, lines don't have to cross. If you can imagine in the classroom, if I drew a line from one corner to the other, and then drew another line from here to the same position on the back wall, those lines wouldn't cross, would they? Hello, miss.
Hello, I brought the student here.
Dulla, he was missing. Right, come on, Dulla, take a seat. Dulla, can you sit here for me? Is that all right? Okay. So it's important to know that sometimes when we're looking at three-dimensional vectors, if we've got 2 lines, they don't always cross. So have a look at this little diagram. So it's 3-dimensional, and you can see that we've got 2 vectors in the classroom, or 2 vectors in a room, but they don't cross. Unlike simultaneous equations of graphs, where if they've got different gradients, doesn't matter where, if 2 lines have different gradients, they will always cross at some point. It doesn't have to happen in vectors. So we've got to work out where they cross and if they cross. So that's what we're going to be able to look at today. Right, moving on, let's have a look at a couple of examples then. So what we're going to do is we're going to show that the lines with these equations intersect. Once we've worked out whether or not they do intersect, we're going to actually see where they intersect as well. Okay, I'm going to demonstrate the process for you on the board, and then you guys are going to have a go at an example on your whiteboards, please. Okay, so if I've got these 2 equations of my vectors, I find it easier, and I'd like you guys to do this as well, I find it easier to rewrite these in column vector format. Are you all happy with 3i, 8j, and minus 2k being 3, 8, and minus 2? You're all happy with that? Yeah, brilliant. Okay, so I've rewritten both of my vectors so far in column vector format. Now once I've done that, simultaneous equations, it works because we're literally seeing where, have a look at this diagram here, we're looking at where one graph intersects with the other. At that point, which is just here, one line has got the same x-coordinate and the same y-coordinate as the second graph. You should all know that. Right. Similarly, when we're looking at vectors, we're going to set the x-coordinate and the y-coordinate the same. We're then going to see whether or not the z-coordinate works for both of them. If it does, they intersect. If it doesn't, they don't intersect. So have a look at the following. The x, y, and z coordinates of these vectors, are you happy that I could write this one as 3 plus 2t for the x coordinate? I could write it as 8 minus t for the y coordinate. Mo, what would the z coordinate give us?
Minus 2 plus 3t.
Minus 2 plus 3t, perfect. And if we're doing the same thing for the second vector, for the second equation, what would I get for the x values?
7 plus 2s.
Right, 7 plus 2s is the first one. How about for the y's?
4 plus s.
4 plus s, easy, and for the z's,
3 plus 4s.
3 plus 4s, perfect. Are we happy with that so far? Now, as we said before, in 2-dimensional graphs, the x and y coordinates are equal for those 2 graphs. So what I'm going to do is I'm going to have a look at the x coordinates and the y coordinates. This is the expression that I've got for my x coordinates, 3 plus 2t. The second graph, it's 7 plus 2s. If we know the x values have got to be equal, I'm going to set the x values equal to each other. So the 3 plus 2t is equal to the 7 plus 2s. I'm literally saying that the x values must be the same. Okay, done. I'm now going to do the same thing for the expressions in terms of t and s for the y coordinates. Okay. Are you happy that this y coordinate, 8 minus t, the next y coordinate, 4 plus s? Happy? Yeah. So we're going to set those equal to each other. We're saying that one y coordinate, the y coordinate of the first equation, is equal to the second y coordinate of the second equation, like so. Once you've generated your two sets of simultaneous equations, we're going to solve them like we would normally solve simultaneous equations. We need to get either the s's or the t's to have the same coefficient. Now, with this one, what I can see is that if I was to use these are the x values, we've set the first x value equal to the second x value. 3 plus 2t is equal to 7 plus 2s, that's it. For the y coordinates, 8 minus t, which is from the first set of equation, is equal to 4 plus s, which is from the second equation. We've set them equal to each other. On your whiteboards now, I'd like you guys to have a go. It's just the same sort of thing from GCSE. I want you to try and solve these two simultaneously and show me what values you get for s and t. On your whiteboards, you've got 1 minute. Time starts now. I'm really sorry, because because Mohammed's not going to be in today, you have to be working on your own. Is that all right? So one of the activities you're doing in pairs. Oh, don't worry about it. You're late again. I know, I saw Miss Beck.
Keep facing the front.
"30 seconds left. Come on." I'll give you another 30 seconds because a few of you are only about halfway there. Yeah, you can rearrange them if you want. You can just keep it. There's that, and there's that. Okay, because you've multiplied this one by 2 perfectly. Now what I'm going to do is I'm going to do the bottom one, take away the top one. 2s minus 2s is no s. 8 take away 7 is going to leave us with
8 take 1.
8. Oh, was that a 1? Sorry, like I said.
No, 8 take away 7.
Yeah, that's going to leave us with 1. Yeah. Next bit, if I've got minus 2t and I take away from that 2t, how many t is my left?
Minus 14.
Okay, so I'm going to be left with a minus 4t. And if I do 16, take away 3, go. Okay. Now I need you to rearrange this, get the 4t was the positive side, and move the 1 to the other side as well. Perfect. Okay, now once t is 3, how do you now solve this to work out?
Sub it back in.
Sub it back in, good lad. That looks interesting. Good looking at it. You will have made a mistake there. Yeah, you should times it by 2. Okay, 2, let me just check this one here. That should be minus 2t and 16. Okay, so what did you do next? Okay. Is that the first equation? That cancels that out. Right, perfect. Now the only thing you've done wrong then, is that a positive 15 or a negative 15? So when you move it to that side it becomes negative. Change that to negative, fix it. Okay, that's enough time. Boards up for me, please. Perfect, perfect. Perfect. Well, you've only, oh no, it's next, sorry, it's fine. Yeah, good girl. I know you're fixing yours. Good lad, Abdullah. You messed up? Don't worry about it. We'll fix it in a second. Just see where you messed up. We'll come back to it, don't worry. We'll come back to it. Right, I'd like to move on, but as about 80% of you found out, use this, can't I? As about 80% of us found out, when we solve these simultaneously, we get the values of s equal to 1, and we get the value of t equal to 3. If you didn't get it right that time, don't worry. I'll go through another example in a minute about solving simultaneous equations once more. Right, happy so far? So we've just found out that in order for the x-coordinates and the y-coordinates to be equal, In order for that to happen, the value of s has to be 1. Now s was the value that we got for our second equation. In order for it to be true as well, t must equal to 3, which is what we got for our first equation. Okay, we've got t is for the first, s is for the second. Now what part, x, y and z coordinates, what part have we not looked at yet? We've not looked at the z's. Okay, we've solved the x coordinates simultaneously. We've solved the y coordinates simultaneously. What we're now going to look at is solving the z coordinates simultaneously. Now, if, and only if, those lines intersect, when we substitute in the s and t values, it's going to come out with something that is true, something that is correct. Let's have a look at it. So, we've looked at the x and y bits, as we've already seen. Move on a little bit faster. Now, this value here, hopefully you can see, has been taken from the z coordinates. So minus 2 plus 3t, that's the z coordinate of the first equation, and 3 plus 4s, z coordinate of the second equation. I'm going to substitute in, for the first and second equations, the value of t and s. If they intersect, then we will find that the left-hand side is equal to the right-hand side for the s and t values that we found. If the lines do not intersect, then we'll get one thing is not equal to another thing. 4 equals to 7 is false. Right? Let's see what we get then. So I'm going to substitute in that t is equal to 3. I'm going to substitute in that s is equal to 1. I get minus 2 plus 9 is equal to 3 plus 4. Work it out. You can see we've got 7 is equal to 7. If you find that one side is equal to the other, after substituting in the s and t values, they do intersect. As we say, if they don't equal to each other, they don't intersect. And that's what you need to be able to see, whether they intersect. Now, once we've worked out whether or not they intersect, the next thing we've got to do is find the actual specific point, the point of intersection. Now, this should be quite nice and easy. We've worked out so far what the value of t is and the value of s. Only when t is 3 and only when s is 1 do those lines intersect. Dole, what do you think I'm going to do with t is equal to 3 with this equation at the top? What could I do? Jerry?
To do what?
Well, I'm going to have to see what points these lines intersect. And I've got so far that they definitely intersect at the point where t is equal to 3. But now I need an actual coordinate, a firm value. These lines intersect at that point. Now, typically, when you get given t is equal to 3, x is equal to 4, y is equal to 5, what do you do with it?
So,
You've got to substitute it in somewhere. Are you happy? T value of 3 can only be substituted into the first equation. Are we all happy that the s value, s is equal to 1, can only be substituted into the second equation? Right, I'm going to substitute it into both of them. I'm going to show you what I get. Right, so we're going to calculate the position vector. That's the point of intersection. That's how I think of it. This is my first equation. Again, I've written it in column vector form because I find it more visually pleasing. It's easier for me to see. I'm going to substitute in that t is equal to 3. There we go. Now, when I do that, I'm going to multiply these values by 3. You know the rules of vectors. Then we add them together. I've got that the equation R, when t is equal to 3, we have this point, 957. That is the point. That must be the point of intersection. To prove that it's true and to check that you've got the answer correct, for the second equation, 7i plus 4j plus 3k plus s outside of 2i plus j plus 4k, again, written in column vector format, substituting the value that s is equal to 1, add them together, 957. Can you see that both of them have the same point? And that is how we find the position, the point of intersection in three-dimensional vectors or three-dimensional lines. How do you find that? Right, we're on your whiteboards. I know a couple of you found that a bit tricky. On your whiteboards, I would like you guys now, I'm going to give you 5 minutes to have a go at these 2 questions. I want you to see if you can work out the points of intersection between here and here. The first thing you need to do is work out whether they do intersect. And once you have worked that out, the next step is to find the point of intersection. 5 minutes, have a go. Time starts now.